So in this video, we're going to look at the integral test and the geometric series test. Now, for the integral test, we are going to essentially treat the formula for the terms of our sequence, of our series, as a function. Now, typically, we want this function to be continuous and decreasing. If it's increasing, then we're not going to be able to, it's going to obviously diverge. We won't need to bother with this. The second thing, of course, is that if we're starting at 1, we're going to integrate from 1 to infinity, since it's an infinite sequence, infinite series. And we want to determine if this improper integral is going to converge or diverge. Now, we also need the function, when converted into a continuous variable, to be continuous. We don't want it to have lots of breaks. Typically, if we have an alternating component, you're not going to be able to use the integral test, because then exponentials, particularly raised to some negatives, raised to some power, they're well defined when you use integers as powers. They're less well defined when you use continuous values as the exponents. And so if you have an alternating piece, you can't use this. You will have to use the alternating series test. But if your terms are basically all positive and therefore going to 0 through positive values, then you can apply the integral test. Essentially, what the integral test is doing is it's estimating the area under this continuous curve. You can think of the integer values for n equals 1, n equals 2, and so forth as like our Riemann sum approximations of the area. So they're like little rectangles with widths of 1. And therefore, we're not going to get the exact value for the sum of the series. But if the sum is going to converge, so will the area, and vice versa. And if the sum is going to diverge, then so will the area under the continuous curve. So that the fact that it's an approximation means that I can't get the exact value, but I can at least say converges or diverges. There is also an error formula for the integral test that we will look at in another video, along with the error for the alternating series. Now, the harmonic series we've talked about several times in previous videos, and we've simply kind of asserted that it's going to diverge, but the integral test actually allows us to prove this. And the very simple fact is that if we treat the continuous function as essentially 1 over x, when we do this antiderivative, we end up with log. And when we let this upper limit in our improper integral go to infinity, log of infinity is infinity. And therefore, it's going to diverge. The log of 1 is 0 in this case, but even if it was some other starting value, it would be a constant and it would still depend on what this final term is doing. So even though these individual terms are going to 0, we see that if it's not alternating, it's not going to 0 quickly enough to actually converge to some finite value. Now, we can actually use the integral test to prove the p-series test that we talked about before. When p is not equal to 1, that would be our log exception, then what we're essentially going to get is a power series, a formula using the power formula, the antiderivative of x to the n, essentially. Now, if p is bigger than 1, then this power is still going to be negative. If p is less than 1, then this power is going to be positive. And that's where the distinction comes. If p is a third, you end up integrating to get infinity to the 2/3 power. It's the positive power, it's going off to infinity. But if n for example, is 2, then you're going to get a negative power still be x to the -1. And this will be true anytime p is larger than 1. and infinity will then be in the denominator, and then that will converge. This should actually, yeah, the negative times the negative is 1. So that's sort of the key dividing line here. So even though the formula itself for p equals 1 turns out to be something slightly different, if p is 1 or smaller, it will diverge. And if it's bigger than 1, it will converge. But we can prove this using the integral test. Now, the integral test can also be used for other things. Now, they can be a little bit tricky in the sense that you may have to do integration by parts or things like that. But as long as they don't have factorials in it, then at least in principle, you can do, or n to the n, you can at least do the integration. So in this example, I rewrote my formula here as x, which was my n in the numerator, and then 2 to the negative x, which was 2 to the n in the denominator. And if I integrate this, I have to do this by parts, and you get this expression when you do that. And then you let your limit, actually, these should be b's here now. You let your limit go to infinity. Now, all of these, of course, where you're just plugging in the lower limit 1, they don't matter. But here, you're going to have, in this expression, you only have a b in the denominator. So that's going to 0. That's good. This one, you have a b in the numerator and in the denominator. You can do L'Hopital's rule to turn this into -1 and then 2 to the b times another log 2. And then you'll have only the 2 to the b left in terms of the infinities. And then you can see that that will also converge to something. It'll actually go to 0. And so this will go to 0 and this will go to 0, meaning that you get a finite value for this area under this curve, and it does in fact converge. The integral test can be tricky for some of these, and we will find other tests that we can use for a lot of these cases that don't require us to do integration by parts. But when in doubt, if it's a function you can integrate, great. But again, keep in mind, you can't integrate things that have alternating components in them. And as I mentioned, we don't have ways to do factorials. There is a way that you can approximate a factorial, but there are better ways to work with problems that have factorials. And n to the n would also be sort of a mess. Not necessarily impossible, but not something that you really want to work with. There are better tests for that. Okay, and then the second one that we're going to talk about in this video is geometric series tests. Now, typically geometric series are often done very early in a chapter on series tests because they're simple, and like the telescoping series, they actually can tell you the actual limit of the series. And the test basically says that if this multiplier here that's being raised to the power, if that is the absolute value that is less than 1, then the series will converge because you're multiplying by a number smaller than 1 over and over again, and therefore it's getting smaller as it keeps, and smaller pretty quickly, exponentially as you keep multiplying. If this multiplier is greater than or equal to 1, the series will diverge. Now, when it's -1, it won't blow up to infinity. It will wiggle back and forth between a sum of 0 and 1, but that's not going anywhere. It's not converging to some specific value. When it's 1, +1, or any r bigger than 1, then the terms will, in fact, the sum will go to infinity. If it's negative, they will alternate between positive and negative infinity, but they'll keep getting bigger. If r is positive and bigger than 1, then it will obviously blow up. But even if you're just adding up 1, 1, 1, 1, 1 forever, you're going to get an infinity. Now, in the case where it converges, then you can use this formula, the first term, this in front of the geometric part, and then 1 minus that ratio, that will give you the sum of the infinite series. So let's look at a couple of examples for this. Now here, we're taking the sum, and again, geometric series often start counting with n equals 0. That's important if you're going to use that sum formula, because you actually have to, that formula depends on you starting at n equals 0. But if you're just testing for convergence or divergence, the value it starts at is not that important. So for this one, we are looking at pi over 4 raised to the n. Well, the question is, what is pi over 4? Is it bigger or smaller than 1? Well, pi is less than 4, so we're dividing a smaller number, 3.14, by 4, and so that is, in fact, less than 1. In fact, if you check it in your calculator, it's about 0.78 and change. Therefore, this ratio is less than 1, and it will converge. And you can find the value it converges to by doing a little bit of arithmetic with our sum formula. Now, in the second case, we're looking at, they started counting at n equals 1. And so if I want to calculate the sum, I actually need to rewrite this so that it starts at n equals 0 so that my formula will work. And essentially what I'm going to do is I'm going to re-index. If I take 1 away here and start at 0, I have to put 1 back up here so that this power will be 1 on the first term. Now, what that means is that I just have an extra copy of 2 over e floating around, and so I can pull that out front to be my a. So my a is going to be 3 times 2 over e, or 6 over e. And then I now have my formula in the form I can use my sum in. And then if I just check, e is in fact bigger than 2, so 2 over e will converge, and therefore I can actually apply this formula, the sum formula, to get the sum of my sequence. So my 3 times 2 over e is 6 over e. I put my 2 over e in the denominator, I do some arithmetic, and I end up with a sum of about 8. On the other hand, if I use pi over e, e is not as big as pi. Therefore, this ratio is going to be larger than 1, and therefore it's going to diverge. All right, now in the next video, we're going to look at the root test and the ratio test. And the ratio test is the one that you want to use particularly for factorials.